Let's begin with a sentence that sounds almost absurd. What if light is older than the universe? At first, that feels like a mistake. The universe, according to modern cosmology, is about 13.8 billion years old. Light exists inside the universe. Stars produce light. Galaxies shine. The cosmic microwave background is ancient light traveling through space. So how could light possibly be older than the very universe it moves through? If that statement were literally true, it would mean something is fundamentally broken in our understanding of physics. It would mean our timeline of cosmic history is wrong. It would mean that time itself, the framework we use to measure, older and younger, might not be what we think it is. But before we allow dramatic conclusions, we need to slow down and ask a very careful question. What exactly do we mean by older? When we say one thing is older than another, we are comparing durations in time. A tree is older than a leaf because it has existed longer. A mountain is older than a building because it formed earlier in history. All of this assumes something very simple. Time is flowing in the background like a universal clock, ticking the same way everywhere. But modern physics has already taught us that this assumption is not entirely correct. According to Einstein's theory of relativity, time is not absolute. It does not tick the same way for everyone. It stretches and compresses depending on motion and gravity. Two observers moving differently can disagree about how much time has passed. That alone should make us cautious about using words like older without thinking carefully. Now consider something even stranger. Our best theory of gravity, general relativity, tells us that time and space are not separate from the universe. They are part of it. They are woven together into spacetime. And according to the standard cosmological model, spacetime itself began in the Big Bang. That means time did not exist before the universe. Time began with the universe. If that is true, then asking whether something is older than the universe becomes a confusing question. Older requires time. But if time began at the Big Bang, then there is no before, in the usual sense. It's similar to asking what is north of the North Pole. The question sounds grammatical, but the concept breaks down. So when someone says, what if light is older than the universe? The real issue may not be light at all. The real issue may be our understanding of time. Are we assuming that time is a kind of container in which the universe sits? Or is time part of the universe itself? If time is part of the universe, then comparing something to the universe in terms of age might be like comparing a wave to the ocean and asking which came first. Already we can see that the question is not simple. It forces us to examine assumptions we rarely notice. And that is where real physics begins, not with dramatic claims, but with careful thinking about the meaning of the words we use. Now let's clear away speculation and focus only on what we actually know from observation. We know the universe is expanding. This is not philosophy. It is measurement. When astronomers observe distant galaxies, they see that their light is stretched toward the red end of the spectrum. This redshift tells us those galaxies are moving away from us. And not just a few of them, almost all distant galaxies are receding. The farther away they are, the faster they move away. This pattern strongly suggests that space itself is expanding. If we imagine running this cosmic expansion backward, like reversing a film, everything would move closer together. Galaxies would compress. Temperatures would rise. Densities would increase. Continue that backward far enough, and the universe becomes extremely hot and extremely dense. This is what we call the early universe. Now here is something precise and important. The early universe was not full of stars and planets. It was too hot for that. It was so hot that atoms could not exist. Electrons were not bound to nuclei. Instead, the universe was filled with a dense plasma, a mixture of charged particles and radiation. Radiation means light. So yes, light existed very early. But we must understand the conditions carefully. In that plasma state, light could not travel freely. Photons were constantly scattered by free electrons. Imagine trying to walk through a dense crowd where you bump into someone every step. That was the situation for light. It existed, but it could not move far without interacting. Then something crucial happened. As the universe expanded, it cooled. After about 380,000 years, temperatures dropped enough for electrons and protons to combine and form neutral hydrogen atoms. When this happened, photons were no longer scattered constantly. They could finally travel long distances without interruption. That ancient light is still traveling today. We detect it as the cosmic microwave background radiation. It fills the entire sky. It is incredibly uniform, with tiny temperature fluctuations that match our predictions of early cosmic structure formation. This is not speculation. Satellites like COBE, MAPE, and Planck have measured this radiation in extraordinary detail. So what do we actually know? We know light existed in the early universe. We know that after 380,000 years, it began traveling freely. We know we can still measure that light today. But notice something important. All of this occurs after the universe begins expanding. There is no observational evidence of light existing before the Big Bang. In fact, the phrase, before the Big Bang itself, is problematic in standard cosmology. Our equations allow us to trace expansion back to a very early state, but as we approach extremely small times, around 10 nanoseconds, our current theories break down. That boundary is called the Planck time. Beyond that, we do not have a confirmed physical theory. So what we know is limited to what our equations and observations support. And within that framework, light emerges inside the early universe, not before it. The idea that light might be older than the universe is not something supported by current evidence. It is a conceptual puzzle, not an observational result. And recognizing the difference between evidence and speculation is one of the most important habits in physics. To understand why the question of light being older than the universe is so confusing, we need to examine the nature of light itself. Light is familiar in everyday life. It moves from the sun to earth. It reflects off objects so we can see them. It travels at a speed of about 300,000 kilometers per second. That seems simple. But in the framework of modern physics, light behaves in ways that challenge our intuition. According to Einstein's theory of special relativity, the speed of light is not just fast, it is absolute. No matter how fast you are moving, if you measure the speed of a photon, you will always find the same value. This constancy leads to consequences that are deeply counterintuitive. When objects move at speeds approaching that of light, time slows down for them relative to an outside observer, and distances contract in the direction of motion. These are not illusions. They are physical effects confirmed by countless experiments with particles moving near light speed. Now consider what this implies for light itself. Light travels at the ultimate cosmic speed limit. Mathematically, the equations of relativity predict that along the path of a photon, the passage of time is zero. That means from the moment a photon is emitted, perhaps billions of years ago, to the moment it is absorbed, no time elapses along its trajectory. The photon does not experience aging, and in a strict sense, it does not experience time at all. This does not mean that photons have consciousness. They do not observe or feel. But the mathematics suggests that the concept of elapsed time simply does not apply to them. If a photon travels from a distant galaxy to Earth, it may have taken 13 billion years according to our clocks, but for the photon itself, that journey is instantaneous. This is a mind-bending idea because it challenges one of our most basic assumptions, that time is a universal backdrop against which all events unfold. It is at this point that language begins to fail. When we ask whether light is older than the universe, we are using the word older in the way humans normally use it. But if time does not exist for light, then does the question even make sense? Can we assign an age to something for which time does not pass? From our perspective, we can measure the time it takes for light to reach us. From the perspective implied by the photon's trajectory, time is irrelevant. This difference exposes the subtle limitations of our intuition. Furthermore, light is not just a particle moving through space. In quantum field theory, light is an excitation of the electromagnetic field, a ripple in a fundamental fabric of reality. Fields like this are not passive entities sitting inside space. They are part of the very structure of reality. The electromagnetic field existed even when there were no photons as discrete particles. Photons are manifestations of this underlying field interacting with spacetime. This suggests that light, in its most fundamental sense, is tied to deeper aspects of reality that may predate the structured universe we see. So when we ask whether light is older than the universe, we are forced to confront the possibility that our conventional concepts of age, duration, and temporal order may not apply at the most fundamental levels. The photon teaches us that time is not absolute, that our intuition about before and after can break down, and that light, in its deepest sense, is intertwined with the structure of reality itself. Our everyday ideas of chronological order are insufficient to describe the strange, timeless behavior of the universe at its most fundamental level. Now we step into even deeper questions, the ones that challenge our assumptions about time itself. In classical physics, time seems obvious. Seconds tick by on a clock. We remember the past and anticipate the future. We measure durations, calculate ages, and organize events along a timeline. But what if time is not fundamental? What if it is an emergent property, something that appears only under certain conditions? Modern theoretical physics suggests that this might be the case. Time as we experience it may not exist at the most basic level of reality. It could be a macroscopic effect arising from more fundamental processes, just as temperature emerges from the motion of countless molecules. To illustrate this, imagine a container of gas. Temperature is an emergent property of the average motion of the molecules inside. If the molecules stop moving, temperature ceases to exist. It is not a property of a single molecule, it is a statistical phenomenon. Similarly, time could emerge from the interactions of a vast number of quantum states. On the smallest scales, there may be no ticking clock, no flow from past to future, only a complex network of relations that give rise to what we perceive as time. If time is emergent, then the traditional notion of before the universe may not make sense. The Big Bang is often described as the beginning of time. In classical general relativity, time and space are intertwined in a four-dimensional fabric known as spacetime. As we approach the singularity at the Big Bang, our equations predict infinite density and curvature. But these predictions signal a breakdown of the theory. General relativity cannot describe the conditions at extremely small scales. Quantum effects, which dominate at such scales, are not included. Our current understanding fails, and with it, our conventional notions of past and future. Some speculative theories attempt to go beyond this limitation. In models of quantum cosmology, the universe might have emerged from a quantum vacuum fluctuation. But the quantum vacuum is not nothing. It is a seething field of energy, constantly fluctuating. In other models, there could have been a prior contracting universe that transitioned into expansion, a cosmic bounce. In yet other approaches, time itself might be an emergent phenomenon arising from entanglement patterns in a deeper quantum structure. In these cases, asking whether light is older than the universe becomes a meaningless question because both light and time might have emerged together from the same underlying reality. This perspective forces us to reconsider our language. Words like beginning and before carry intuitive meaning in everyday life, but they may not apply at the deepest levels of physics. The human brain evolved to understand a world of objects and events that unfold in time. We think in terms of causes and effects, past and future, yet these concepts might not map onto the fundamental nature of the universe. Reality at the quantum level is stranger than our intuition allows, and light behaves in ways that defy ordinary notions of temporal order. Understanding this is not merely a philosophical exercise. It has practical implications for physics. The behavior of light, its constant speed, and its timeless trajectory in relativity indicate that time is relative, not absolute. If time emerges from more fundamental processes, our attempts to trace the universe's history backward to a singular beginning may be limited by the conceptual frameworks we use. Light, as an excitation of a field that pervades space, may exist in ways that transcend conventional time, revealing the deep structure of reality itself. In confronting these ideas, we recognize that our struggle is not with light or the universe, but with our own assumptions. Light challenges our intuition, and by studying it, we glimpse the possibility that time is not a fixed background, but a property arising from a deeper, more intricate foundation. The universe may not begin in time as we understand it, and light, timeless in its journey, hints at a reality far more complex and astonishing than our everyday experience suggests. The Big Bang is often misunderstood as an explosion in space, like a bomb going off in a room. But this analogy is misleading. The Big Bang was not an explosion in a pre-existing space. It was the expansion of space itself. Every point in the universe moved away from every other point, not because it was thrown into empty space, but because space itself was stretching. There was no outside for the universe to expand into. There was no container holding it. The expansion happened everywhere at once, uniformly, creating the cosmic stage upon which all matter, energy, and light would eventually exist. When we trace the universe backward in time, General relativity predicts a singularity, a state of infinite density and temperature where the known laws of physics break down. This singularity is not a physical location in space, but a boundary to our understanding. It signals that our current theories are incomplete. Classical physics cannot describe conditions at such extreme scales. At this point, quantum effects dominate, and we do not yet have a fully developed theory that combines quantum mechanics with gravity. This is one of the major unsolved problems in physics. Although we often speak as if time began at the Big Bang, this is based on extrapolating our equations into regions where they are no longer reliable. Time, as we know it, may not exist in these earliest moments. Asking what happened before the Big Bang may not be meaningful in the context of classical cosmology. It is similar to asking what is north of the North Pole. Language and intuition break down when applied outside the context in which they were developed. Despite these uncertainties, we have observational evidence of light interacting with the universe shortly after the Big Bang. The cosmic microwave background radiation is a snapshot of the universe approximately 380,000 years after the initial expansion. Before this time, photons could not travel freely because they were constantly scattered by charged particles in the hot plasma. Only when neutral atoms form could light escape and propagate through space. This sets a clear timeline for the earliest detectable light within our universe. Speculative theories go further. Some suggest the universe emerged from a quantum vacuum fluctuation. The quantum vacuum is not nothing in the classical sense. It is a dynamic, fluctuating field filled with potential energy. In other models, there could have been a pre-existing contracting universe that transitioned through a bounce to create our current expanding cosmos. Alternative theories even propose that time itself emerges from the relationships between quantum states rather than existing as a fundamental dimension. If time is emergent, then concepts like older and younger may not apply in any straightforward way. The behavior of light is central to these discussions. Light is not merely a particle traveling through space. It is an excitation of the electromagnetic field, which is part of the fabric of reality itself. The speed of light defines the causal structure of spacetime, and photons, moving at this ultimate speed, experience no passage of time along their trajectories. This means that in a sense, light is timeless. Its behavior forces us to reconsider what we mean by age, duration, and chronology at the most fundamental levels of physics. By understanding the Big Bang as an expansion of space and recognizing the limits of our current theories, we see that our intuitive notions of time and order may not fully apply to the earliest moments of the universe. Light, emerging from the hot plasma and traveling across the cosmos, serves as both a witness and a probe of these deep mysteries. Its properties challenge our assumptions and invite us to rethink the concepts of beginning, duration, and existence. At the edge of our understanding, we find that the universe is stranger and more subtle than everyday experience would suggest, and that our journey to comprehend it is ongoing. With light as one of the clearest guides in quantum field theory, light is not merely a particle moving through empty space. It is an excitation of the electromagnetic field, one of the fundamental fields that permeate the universe. Fields like this are not passive backdrops. They are active participants in the dynamics of reality. Photons, the particles of light, are ripples in this field. They are created and annihilated as the field interacts with matter and energy. This perspective changes the way we think about the existence of light. It is not just traveling through space, it is an expression of the underlying structure of reality itself. This realization leads to an even more profound question. If light is an excitation of a fundamental field, then perhaps the field itself is more fundamental than the spacetime in which we observe photons. In some modern theoretical models, spacetime may itself emerge from a deeper quantum structure. Space and time might be secondary, arising from relationships between more basic entities, such as quantum bits of information or patterns of entanglement. If this is the case, then light is intimately connected with the very fabric of existence. It is not simply an object within the universe. It is tied to the deeper rules from which the universe arises. Considering this, asking whether light is older than the universe becomes even more subtle. Light as we perceive it, photons traveling through space, emerges after the universe has cooled and matter has formed. But the electromagnetic field, which gives rise to light, may be part of a more fundamental layer of reality that predates the formation of spacetime itself. This distinction between photons and fields is critical. It suggests that the concepts of before and after may not apply in the way we intuitively understand them. If spacetime itself is emergent, then all processes that depend on spacetime, including the propagation of light, are also emergent. This perspective challenges our basic understanding of chronology and existence. Our language and intuition are deeply tied to time. We naturally think in terms of cause and effect, past and future, age and duration. But at the fundamental level of quantum fields and emergent spacetime, these concepts may not hold. A photon traveling across the universe experiences no passage of time along its path. The electromagnetic field exists as part of the underlying reality, not constrained by the temporal order we observe. This means that our everyday notions of age, sequence, and causality are approximations, valid only within the emergent spacetime of the macroscopic universe. Moreover, the interaction between light and spacetime is not one way. The structure of spacetime affects how light moves, and light, in turn, defines causal relationships within spacetime. The speed of light is the ultimate limit for causality, dictating how information and influence can travel. In relativity, this speed is built into the geometry of the universe itself. It is not merely a property of photons, it is a property of reality. In this sense, light is more than just energy in motion. It is part of the scaffolding of the cosmos, a measure of the very limits of how events can be connected. Understanding light in this fundamental way forces us to confront the limitations of intuition. The familiar ideas of older and younger, beginning and end, are not adequate to describe the universe at its deepest level. Light, as both a particle and a field, reveals the intricate and interconnected nature of reality. It highlights that time, space, and matter are not the ultimate foundations of existence, but emergent features of a far more complex underlying structure. In studying light, we glimpse a reality that is both stranger and more coherent than our everyday experience, challenging us to expand our concepts and rethink what we mean by existence itself. Humans struggle to grasp these ideas because our brains evolved to navigate a very different world. Everyday life involves objects that have beginnings and endings, actions that follow causes, and events that unfold in time. We naturally think in terms of before and after, past and future, older and younger. These concepts are so ingrained that we rarely notice we are assuming them even when we explore the universe. Yet at the fundamental level of physics, these intuitive notions can break down completely. Light is a perfect example of this breakdown. Photons move at the ultimate speed limit of the universe, the speed of light. According to relativity, along their trajectories, time does not pass. From the emission of a photon in a distant galaxy to its absorption in a telescope on Earth, the journey may take billions of years, according to our clocks. But for the photon itself, no time has elapsed. The idea of age loses meaning. The language we use, the words we rely on to describe chronology, fail to capture the reality of light's existence. Our instincts tell us that things move through time, that events happen in sequence. But at the level of photons and fundamental fields, these instincts are unreliable. Moreover, light is not simply a particle traveling through space. It is an excitation of a field that pervades the universe, part of the deeper structure from which space and time themselves may emerge. Some theories suggest that spacetime is not fundamental, but arises from patterns of quantum entanglement or other deep relationships in a pre-spacetime structure. In this framework, asking which came first, the light or the universe, might be a question that does not make sense because both could emerge simultaneously from a more basic reality. Our words are inadequate to describe processes that are not bound by the familiar flow of time. The question forces us to confront our own limitations in understanding. The challenge is compounded by the fact that humans are conditioned to look for causes and effects. We evolved to survive by predicting what happens next, by understanding sequences of events. We instinctively imagine the universe as a story unfolding, where one thing follows another. But at the quantum level, and in the earliest moments of the cosmos, cause and effect may not operate in the same way. Particles can exist in superpositions, entangled across vast distances, and interactions can be fundamentally probabilistic. Light, traveling through a universe where spacetime itself may be emergent, exemplifies this. It operates according to principles that defy ordinary cause and effect reasoning. Our struggle to conceptualize it is a reflection of our evolutionary limitations, not a failure of physics. The difficulty also arises because our perception of time is tied to change. We measure time by motion, decay, and oscillation. Light is change itself, oscillating electric and magnetic fields that propagate through space. Yet at the deepest level, if spacetime emerges from more fundamental structures, even the notion of motion, as we understand it, may be secondary. Time itself could be a macroscopic feature that only appears when complex systems interact in ways that generate the flow we perceive. In that context, light is not simply moving in time, it is participating in the emergence of time, intertwined with the structure of reality. Our struggle to comprehend these ideas reveals the gap between human intuition and the universe's underlying logic. Concepts like older, before, and younger are tools useful in daily life, but at fundamental scales, they may be irrelevant. Light teaches us that reality does not conform to our instincts. It challenges us to think beyond intuitive sequences and linear timelines. By studying light and its behavior, we confront the limitations of our concepts and gain insight into the extraordinary nature of existence. The universe at its core is far stranger than our everyday experiences suggest, and light is a window into that profound strangeness, revealing that the notions we take for granted may not apply to the foundation of reality itself. To consider what would truly challenge cosmology, we need to separate speculation from evidence. Cosmology, as a science, is built on observations, measurements, and the logical interpretation of data. The discovery of the cosmic microwave background radiation, the expansion of the universe, and the formation of large-scale structures all form a consistent picture of cosmic history. These observations tell us that light emerged within the early universe, after it had cooled enough for atoms to form. The photons we detect today traveled through space over billions of years, carrying with them information about the universe's infancy. This is well established and highly precise. However, imagining evidence that photons existed before the universe, or outside the framework of spacetime as we understand it, would require us to revise our models in a profound way. Such a discovery would suggest that the standard timeline, beginning with the Big Bang, is incomplete. It would mean that either our understanding of time is fundamentally flawed, or that the origin of light and the universe is connected to a deeper structure we have not yet observed. The revision would not destroy cosmology in the sense of invalidating all observations. Rather, it would expand the domain of inquiry, revealing a layer of reality that we are only beginning to probe. Science evolves by refining its models, not by collapsing entirely under anomalies. Newton's laws were not destroyed by Einstein, they were understood as approximations valid under certain conditions. Similarly, discovering a pre-universe aspect of light would lead to new frameworks, new equations, and new understanding. The very notion of light predating the universe raises a critical point. Our concepts of time, age, and causality are limited. These are intuitive notions that help us navigate the macroscopic world, but may fail at cosmic or quantum scales. If spacetime itself is emergent from a more fundamental structure, then what we perceive as the beginning is merely a boundary where our current models apply. Photons might exist in this deeper structure in ways that make the question of older meaningless, because the timeline itself emerges with the universe. This scenario emphasizes that challenging cosmology does not necessarily mean refuting it. It means recognizing that our current understanding has limits, and that physics is about pushing those limits carefully. Light's unique role makes it central to any discussion of fundamental physics. It is not just energy moving through space, it defines the causal structure of the universe. The speed of light is built into the geometry of spacetime, establishing the maximum rate at which information and influence can propagate. In relativity, this constant connects space and time in a precise relationship, shaping the universe's structure. Because photons experience no passage of time along their trajectories, they highlight the limitations of our everyday ideas about age and sequence. The existence of light challenges us to confront the ways our language and intuition impose assumptions that may not hold at the most fundamental levels. Considering a hypothetical situation in which light predates the universe forces us to confront a larger lesson. Its observations would need to be interpreted within a framework that accounts for emergent spacetime, the interplay of fields, and possibly the fundamental structure beneath the universe itself. The challenge is not just technical, it is conceptual. It would demand that we rethink the relationship between events, the nature of time, and the meaning of existence. Yet even if light did emerge in some form before the universe, cosmology would not be destroyed. It would be extended, refined, and deepened. Science thrives on such questions. They do not invalidate what we know, they highlight the profound mysteries that remain, showing that our models are tools for understanding, not final answers. Ultimately, the question of light and its temporal relationship with the universe illustrates a deeper truth. The universe is more complex than our intuition allows, and our scientific models are provisional yet powerful. They can accommodate new insights without collapsing, provided we remain precise, rigorous, and willing to revise assumptions in the face of evidence.